Hello, in this video we are going to learn how to set up dynamics of non-uniform circular motion. So it is the general motion where speed is not necessarily fixed. So if you remember, if something is going in a circle, the acceleration there's so at any point is in the circle, and here is the center of the circle. There is always a centripetal acceleration, whether speed is constant or not. So this v, and the v is, when v is there, AC is v square over r in magnitude. This is r. But if v is picking up, say speeding up, speeding up case means over here the v is bigger than what used to be over here. In that case, if you look at the tangent here, there is a tangential acceleration in that way, and its value is the rate at which the v is picking up. If v was slowing down, it will still, the magnitude will be this kind of thing, but the direction will be down like this. Okay, so if we know this, let's see how it forces relate to it. So as you know from the second law, we have F net, and usually is external. So we can talk about multi-part object, like a car going around. So we're not looking at the parts of the car like engine applying a force, but the force only from outside the car. All right. So this is a external, all the external forces, adding up all of them in a vector way, and this mass times A. Now this A is vector, so it has a component along that direction and a component along that direction, and there is a component along this third direction, the z direction as well. So here we will we'll use an axis like this. So this one best when we look at it analytically, best to think in terms of components, as emphasized other places. Okay, so this is O, and I like to use a horizontal a time in which the object is horizontally located from the center, so that it's easy to write down. Let's call this x-axis, and if you call this y-axis, then the z-axis is pointed out of page. Okay, let's see. There will be some forces along this. So according to our if the object is moving that way, we will have a AC that way, and if it's speeding up, it's going to be AT will be that way, delta V over delta T. Of the magnitude of that, and if it's speeding up, and it's going to be that way, AT will be same magnitude, delta V over delta T, if slowing down. If the original motion is along that direction, if moving along that direction, if the velocity is a counterclockwise sense. So if I look at this x-axis, this y-axis, this is z-axis. So if I say all the net external and all adding up to along the x-axis, that should give me mv square over r. So I'll get one equation like that. Another equation I'll get is along the y-axis. So I'll have F net external y will be m delta v over delta t. I'll just leave it like that. This will be negative. If this is negative, then it's towards the positive. So I'll just put a negative sign here, so that if this itself is negative, which means slowing down, then I will kill that negative with minus to get positive y component. This is just a detail. If I had used the y-axis in that direction, there will be no minus sign. But so this sign is basically trying to tell you that slowing down or speeding up will be pointed in different directions, and the way I've drawn is speeding up actually negative. AT has a negative y component. Third equation we get along the z direction. There is no acceleration along the z direction. So F net external along the z direction, when I add them up, 0. So these will be 3 equations I'll get. Let's look at an example, and I feel like the simplest example would be like in a pendulum. An example would be there are only 2 forces in the pendulum, so it's very easy to think about it. So say I have a pendulum which is moving in this circle. We'll come back to the pendulum again and again. So this is the maximum, it goes that way, and the maximum it goes that way. We use this as a positive angle and this is a negative angle. You can see this is a counterclockwise, and that's why it's positive, and this is clockwise, so that's a negative. Okay, so this is this will be angle 0, this direction. So this is the center of the circle is going in, and over here is speed is 0 over here, and over here is speed is 0. We just want to pick some arbitrary point and look at what the dynamics will look like. So this direction is up. Well, there is a tangential direction. Let's see if the motion is going up. We're looking as this thing is going up. So it's basically slowing down, which means if a tangent AT will be in that direction. And there will always be A sub C. So these are the 2 acceleration we know. Forces wise, there is a gravity pulling it down. So let's call this angle theta at this point. So you can talk about directions of jet. This is straight down. This is the weight. This is mass m, and along this is tension. So let's see, before, just like over here, we can call this as x-axis, and we can call this as a y-axis, just over there. When it is speeding up, then AT will be that way, and coming out will be z-axis. So when we look at x component, t along the x component, t has the component t, and actually w has component which is this much, and this angle is theta. So this is adjacent of this, so it's going to be, and it's negative. This is where the positive is. This is the origin of the coordinate system. T minus mg cosine theta, and that's equal to m times a sub c, v square over r at this instant. Along y, what we'll get along y is along this direction. T has no component along that direction. And if I project on here, the y is negative. for the weight. So minus mg, and this is the opposite, so mg sine theta equals, and at is going to be m, if you remember, it's going to be minus delta v over delta t, how the speed is slowing down. So this is negative. So let's just call it delta v delta p. So it's going to be, when you solve it, you can see it's going to turn out to be negative. So I don't need to put extra sign here. So this is negative, and mg mass times change in velocity will be negative at this point in time. It's going up. It's naturally, when it's going up, when it's over here, it's gonna slow down. Is delta v is getting less over time, then this is the case. So okay, so and along z, I don't get any influence along z. There's no forces along z. So it's just 0 equal to 0. So these are the two equations, and that we get in a pendulum, which tells us motion at different points. Later on, we're going to look at energy. Actually, next video we're going to look at energy in a circular motion, and then we're going to look at how to work with these equations and get some more out of it when examining pendulum motion. Okay, so next up is video. Next up is energy in circular motion. See you. Bye.